collisions are 2D by its bidimensional effects, but, in themselves, they are one-dimensional. Everything happens along the one line of action. So, we can take advantage from what we learned before. In our last video, Collisions 2D, we used the coordinates x and y of vectors, but defining them from the magnitude and angle of the vector with the x-axis. Also, the angle with the axes can be found easily. In 3D problems, it's much easier to use x, y and z values than in other kind of system of coordinates, and, more practical, for use in computer simulations. For our graphic simulations, we will keep the x and y axes as they appear on paper. We project the z-axis from back to front. The z-coordinate is suggested by the apparent size of the object. As in 2D collisions, collisions 3D are, in themselves, one-dimensional. Everything happens along the one line of action. On planes perpendicular to the line of action, nothing happens. Let's review how we dealt with the general 2D collision. The method will be exactly the same for the general solution of 3D collisions. Before collision, bodies A and B approach each other. Consider the components of their initial velocities. Unit vectors, E and U, are of utmost importance. Everything happens along the direction of unit vector E. After collision, bodies go away from each other. Components along the direction of unit vector U do not change. VE and VBE will change in accordance with a 1D collision, which happens along the line of action, the direction of unit vector E. So the change from the initial to the final velocities of bodies A and B is due to the change in their components along the line of collision, the line of action. These are the steps needed for solving a 2D or 3D collision. Note that, for a 3D collision, you just had a third dimension z, but the method is exactly the same. First, find the angle of attack and define the unit vectors in accordance. Find the components of the initial velocities, along the directions of the unit vectors, u and e. Apply the equations for the 1D collision to the component of the velocities along the direction of unit vector e. At last, add the two components of the final velocities.
Remember, the component of a vector, along any direction, is given by the dot product of the vector and of a unit vector, along that direction. The dot product can be calculated without reference to the angle, as the sum of the product of the corresponding components of the two vectors. The dot product allows to easily calculate the component of a vector, along any direction. First, we need to find the x and y coordinates of the unit vectors, E and U, in order to proceed, operating the dot products that will give the components of the velocities of bodies, A and B, along those unit vectors. Let's apply our method to a 2D collision. We will be ready, then, for the 3D collision. We have all we need. Begin with the vector uniting the centers of mass of bodies A and B. You must find its magnitude, in order to have the coordinates of the corresponding unit vector. It's easy to find the coordinates of the other unit vector, U, suffice to cross the coordinates of E and apply the opposite sign to one of them, in order to have a null dot product between E and U, as they must be perpendicular to each other. Now that we have the two needed unit vectors, we operate the dot product between them and the velocities of bodies A and B. After collision, bodies distance from each other. Component via E is changed as via E final and component VBE is changed as VBE final. We call the equation we deduced in video 4, 1D collision, in order to find the new components of the velocities of bodies A and B and unit vector E. Insert values. Now, we have the components of the final velocities of A and B, along the unit vectors E and U. And, we know the coordinates of those unit vectors. We find the coordinates of the final velocities, in the x and y axes, by operating the vectorial addition. You can figure out if any mistake has been made along the calculations, computing the kinetic energy before and after collision, and check if they make sense. The 2D simulation has been obtained automating the calculations we went across.
Two bodies collide in 3D space. We know, for each of them, the position of the center of mass, the velocity, the mass. We know, also, the value of the coefficient of restitution, CR. Like in a 2D collision, all the action occurs along the line connecting the center of mass of the two bodies, A and B. No interaction occurs in any plane perpendicular to that line of action. Find the coordinates of the unit vectors E, U and O. U and O must be perpendicular to E and perpendicular between them. L is the vector uniting the centers of mass. Dividing by its magnitude, we find the coordinates of E. To find another unit vector, U, perpendicular to E, it's enough to care that the dot product with E will be null. To find the third unit vector, O, we operate the cross product between E and U. Now that we have the three unit vectors, we can find the coordinates of VA and VB, along them, by operating the corresponding dot products. Here you have the coordinate of VA, along unit vector E, via E. Proceed with the remaining coordinates of VA and VB, along all the unit vectors, E, U and O, by operating the corresponding dot products. From the 6 coordinates found, only 2 will change with collision. Those, along unit vector E. Apply the no equations to find v, a, e, final and v, b, e, final. Now, we have everything we need to place numbers in the vectorial equations, which will give us the x, y, and z coordinates of the final velocities of the two bodies. Be careful not to distract yourself and mistake between x, y and z values. As the calculations, although simple and easy, are long, the probability that some mistake occurs is high. So, check the kinetic energy, before and after collision, and see if the values make sense.
This simulation has two balls in a glass box, 1000 pixels wide, 600 pixels high and depth of 600 virtual pixels. No gravity included. Three balls, in a glass box. No gravity included. To include gravity, just subtract the right amount to the vertical velocity, on each frame. It doesn't make much sense to derive a monster formula for the final velocities in a 3D collision, where the independent variables would be the masses, the velocities of A and B coordinates, the vector connecting the centers of mass, and the value of CR. The sequence of calculations can be automated and underlie simulation software as, of course, it has already been done, and has been just done by us.